Okay, I make that 25 past. So hello everyone, I'm Ewan Fraser and I'm pleased to be chairing session 2 on the thermal and thermochemical storage. So yeah, I make that 25 past, so let's make a start. Hopefully everyone's had a chance to go and grab a quick coffee. So just a quick reminder of housekeeping, make sure you're on mute and your camera's off unless you're presenting. And I'll be giving the presenters a 5-minute warning, hopefully be wrapping up around then anyway to give us a chance for a couple of minutes of questions, but I'll give that verbally. So without further ado, I'd like to introduce our keynote speaker for the session, Professor Christos Markides from Imperial College. Thank you.
Hi there, good morning. I hope you can hear me and see me. Is this okay?
Yes, we can hear you.
All right, perfect. And I will just share my screen and maximize the presentation. So please let me know. You should be able to see my slides now.
Yes, we can see them now.
Okay, so first of all, yeah, it's a pleasure to be with you. Yeah, so my talk, for those of you who invited me, thank you. It's not actually on thermochemical energy storage, it's on thermomechanical energy storage, which I've been told sort of features a little bit less in the CDT. This may or may not be true, I'm not entirely sure, but basically my talk is going to be on systems which involve heat exchange of some form, so thermal energy conversions, and basically that also involve kind of mechanical systems. So both. Yeah, I think I'll sort of go straight into the presentation, given that we don't have a lot of time. So the first thing that I always say in these kind of presentations, and I'm sure I'm preaching to the choir here, but they have to be careful. That when we speak about energy storage, we don't necessarily only mean electricity storage, right? So energy, of course, is is a vector that can take many forms, and electricity is only one of those forms. And dare I say it, it's not even the largest consumed energy source, for example, in the UK or even in Europe. It's actually heat, which is the largest in terms of pure joule for joule. So we have to be very careful when we're looking at energy storage to consider aspects and elements that go outside of storing electricity and potentially also outside of using and consuming electricity. And this is important because one of the strengths of thermomechanical energy storage systems is that they can combine and they can integrate both thermal interactions with external sources and sinks and electrical interactions with external sources and sinks. As you can imagine, that this gives these systems a lot of flexibility. Okay. Now, we know, and I'm not going to go into the details, that of course, as renewables penetrate the grid, and they continue to do so, and they have been doing for some time now, the role of storage basically increases. And there are many, many different types of storage, and I'll get to that in a minute, but there's no one solution kind of fits all. So people talk about the mix of solutions, and there is a role for systems that are based on thermomechanical principles that I'm going to present in a minute. Okay, so it's part of the solution that would allow us to have significant penetration of renewables into our grid. But one of the important things to realize, and this is what I was sort of trying to get to in the previous bullet point, is that, as I said, there isn't a single type of energy storage. Sometimes you need to do something called power management. As I said, I'll come back to this in a minute, but just at a high level, which is sort of short-term things, right, of the order of seconds, minutes, right, tens of minutes, half an hour, whatever. But sometimes you need to store energy for very, very long periods of time. So we could be talking hours or even over days or weeks or even months. And sometimes people talk about interseasonal storage. So you could be storing, across seasons. The other thing that we need to also remember is that depending on the application, you might need something relatively small, right? And you might need something which is what we refer to as grid scale or bulk storage, where you store over the order of hundreds of megawatts or gigawatts in terms of the capacity of the plant. So sometimes batteries are a reasonable solution, but sometimes batteries are not really well placed for what we need to do. And this is really where my kind of presentation is pitched. Okay, and I already talked about, what is thermomechanical energy storage, right? It's any technology that involves both thermal and mechanical energy exchanges. And this is what I was sort of getting to in my previous slide. On the vertical axis, we have the duration of storage, right? And on the horizontal axis, we have the size of the plant, let's say, right? And I think the major things to kind of distinguish in this plot is in sort of things which store and discharge electricity, when we're focusing on electricity here, at a time scale which is of the order of minutes, tens of minutes, hundreds of minutes, or thousands of minutes. So basically inside that red box, right? So anything above this sort of arbitrary vertical line. And that type of application is called energy management rather than power management, which is basically short duration stuff, okay? So we're going to be focusing on this in this particular type of application where we need to store for long durations. Now, what happens once you start looking at different technologies that are able to do this? And this is a common plot that you'll find in the literature. This is one of our own, but you'll find many of these in the literature. Typically, there's a sort of a discharge power rating for the plant, right? So this is how many watts it can deliver when it's discharging, and this is the energy capacity of the plant, okay? And really what we're saying is we want to be in the sort of top right-hand side corner over here, right? So we want to have large plants that are able to, let's say, store power from whole wind farms, right? So this is not just, like a battery in your phone. This is like a huge power stations with, right, thousands of megawatt hours of energy stored. And we want to be in this sort of time scale, of days or weeks of storage, which puts you in this top right-hand side over here. And the thing that you see very quickly, and I've sort of put the common things that you'll find in the literature, right? So lithium-ion batteries, vanadium flow batteries over here, so flow batteries. They start to kind of, these sorts of applications start to go outside, right, of the range of applicability of these technologies. And if you look in the literature, then there are a number of, let's say, usual suspects that come up when you're looking at these types of very large scale and very long duration electricity storage applications. And they are thermomechanical systems. And they generally are classed into, I should also say that there's pumped hydro. So pumped hydro energy storage. This is not a thermomechanical technology, but it's sort of here because it's, of course, the one which is most common and commercially available. But there's basically three technologies that we're going to look at very quickly, which is compressed air, liquid air, and pumped thermal. Okay, and these are the technologies that sort of appear up on this in the applications that we're interested in. So I mentioned very briefly pumped hydro, right, is widely used, but there is an issue with pumped hydro. I mean, one could say, well, why don't you just use pumped hydro? And the reason is because, it does require certain geographical features, right? And so it's not always applicable locally, right? And why don't we just use batteries? And the answer is batteries are not really suitable, right, for energy management applications. So basically very long durations. Another thing about batteries that I didn't mention, I'll throw it in now, is that they typically last for of the order of thousands of cycles, right? So they typically have lifetimes, right, which are maybe 5 to 10 years, depends on how often you use them and what sort of application it is. But we're talking here about systems which are thermomechanical, so basically like power stations, so they can last 30 years or more, okay? So flow batteries are an option, so they go to slightly larger scales on, say, lithium ion, but they do have high costs. They are at an early stage of development, and they do have lower lifetimes than thermomechanical systems. So we're looking at thermomechanical systems for these reasons, okay? And as I mentioned, there are a number of them: compressed air, liquid air. There's also electrical heating. So you use electricity to heat through an electrical heater, and then you drive some kind of thermodynamic power cycle to turn that heat back into electricity. And there's pumped thermal that I mentioned. But of course, in each one of these 3 or 4 categories, if you like, there are subgroups, right? So there's different types of compressed air, different types of pumped thermal, and so on and so forth. I don't have the time to go into it, but I just wanted to give you a feeling, right? That there are a number of options in terms of the technology. And within each type of, let's say, class or type of system, there are, again, a number of variants. Okay? And some of these, by the way, already exist, right? So there are two, in fact, compressed air energy storage systems in the world. This is one which is in Germany, and you can see here the size and some pictures. Typically, these compressed air energy storage systems involve, at the very basic level, right? So we're not going into details. I think this presentation is very, very high level. They involve in one way or another basically compressing air, right? And so using electricity to drive compressors to compress air, which is then stored somewhere. This somewhere could be a cavern underneath the ground, or it could be tanks or whatever. And then when you need the electricity back, you basically discharge this high pressure air through a turbine, right? And you generate the electricity, right? So this is something called the abatic compressed air energy storage. And there is a sort of a variant of this. There are others as well, but another variant is to kind of realize that when you compress something, it also gets hot. So there's a useful form of energy, which is this heat that I mentioned before, that you can also store, and then you can also utilize during the discharge process to basically improve the overall efficiency. So these are variants of electricity, of compressed air electricity storage. Another interesting variant of compressed air electricity storage is something called isothermal compressed air, which effectively involves some process during the compression stage to try to keep the temperature reasonably constant, so not to cause that increase in temperature that I mentioned before. And then, of course, there's isobaric compressed air energy storage, where you use some kind of head or some other means, right, of basically pumping the air into a sort of a constant pressure reservoir. I mentioned also liquid air energy storage, and this is a little bit of a sort of an area of, I would say, maybe UK global leadership, right? So we have a company called Highview Power, which has been developing this technology for a number of years now. Here's a plant of the Highview pilot plant in the UK, 350 kilowatts. You can see there a number of components, but basically the short of this is that you use electricity to liquefy air, and then this is sort of a form of stored energy, and then you can sort of discharge that liquid air and get power. And this is a sort of very simple schematic of liquid air, right? Where you can see that power goes in order to store liquid air, and then you can evaporate it, expand it, and get power out for the discharge when you're delivering the power when this is required. Sort of a side aspect to all of that is something called the Dearman engine, which, so Dearman itself went into administration, which is also a UK company, and then also an area of, let's say, UK leadership here. Because, and this came about because, once you have this sort of liquid air systems, you have something called a cold chain, right? So you have an ability to convert electricity, which is surplus, into liquid nitrogen. And so you have a sort of a whole raft of potential solutions or options of what to do with that liquid nitrogen. And this is an engine that allows you to generate cooling and power at the same time for transport applications. So this is for, let's say, decarbonizing refrigeration trucks and so on. So Dearman itself went into administration, but there's another company called, I think, Clean Cold and Power, which is continuing this development. And then there's pumped thermal electricity storage. This started, there was a company called Isentropic that were based first in Cambridge, and they left, which involves basically compressing or running a forward and reverse Joule or Brayton cycle. What this really means is that you run a heat pump when you have electricity to store hot and cold. So you have two reservoirs, one becomes very hot, one becomes very cold. And once you have this temperature difference, when you need the electricity, you reverse this cycle and you generate power. Okay, and you see here that a number of components in Isentropic's original pilot plant. Now, this pilot plant never run because Isentropic went to administration. It was transferred to Newcastle. And I think in the presentation before me, Dr. Smallbone might have discussed a little bit the further development of this technology at his time in Newcastle, and now I believe in Durham. So he's probably best placed to tell you of the most recent developments of this particular technology. But yeah, so the idea is that you you run a thermodynamic cycle, and you heat one reservoir and cool another, and then you reverse it. Once you have a temperature difference, you can always convert that temperature difference into electricity. This slide is really not, it's not the details of it that I want you to understand, but I think I'm just trying to give you a flavor again for the fact that each technology itself has a number of variants. So just like with compressed air, you had diabatic, adiabatic, isothermal, isobaric, and all these kind of variants. Again, with pump thermal, you have a number of variants. Isentropics technology was a particular type of pump thermal, but there are others. You can see here a number of different configurations that I don't have the time to get into. There are a number of components which are particularly important in this technology, in particular, these reversible compressors and expanders that you need for these systems. And also there was an interest in segmented packed beds. So Isentropic was proposing to use packed beds with gravel inside. Actually, it's not really gravel, it's a particular type of gravel, but that's beside the point. But you can sort of segment these and have different compartments and store different temperatures and many different things and interesting design features. The other thing you could do is, rather than using a gas cycle that I just mentioned, right, for your heat pump and your power cycle, in the case of isentropic, they were using argon, but other people have proposed hydrogen, helium, and other sort of gases. You can have steam. You can have water as your working fluid. So you can run a steam heat pump and a steam power cycle, and this is called CHEST. It's a variant of pump thermal electricity storage. And you can even use transcritical cycles. You might have heard of transcritical CO2 power cycles. Well, you can also have transcritical CO2 heat pumps. And you can run heat pumps and power cycles with CO2 as the working fluid in forward and reverse. Again, this would be an electricity storage system, which I would refer to as pump thermal. It's just that the working fluid is not argon, it's not water or steam, it's supercritical CO2. Okay, so very briefly now I'm going to rattle through a few slides to make a few points that I think for me are very important. The first one of which is, please remember that we're discussing technologies which are large scale and long duration. So you can see here on this chart, I've listed some of the things that I've spoken about, right? So the compressed airs, the liquid air, pump thermal, couple of variants, chest, and so on. You can see here storage durations, right? Up to, beyond 100 hours. And this could be even longer, right? Depends on the designer and what your particular application is, and very large systems. You can see hundreds of megawatts, right? In terms of the applications. And the other thing I wanted to say is, I don't personally believe, and this is a long discussion to have, I don't personally believe that efficiency is really all that important. Most people that work in energy storage will tell you that efficiency in itself is not important. It's really the cost of the systems which is important. And so there's a huge effort, right? And a lot of R&D that goes into, right, identifying technologies with low costs. And there's something called a power capital cost and an energy capital cost. And you want these numbers to be low. And there's a lot of uncertainty around these numbers. And I think I'm just going to come straight out and say that we don't really know what these numbers are going to be. You can see huge ranges there. And the reason for this is because all of these technologies are still being developed. And some of the components that are proposed don't even exist yet, right? So there's a lot of uncertainty in us predicting what the cost of different technologies are going to be in order to perform a good comparison, a fair comparison, but this is the important indicator, not the efficiency of these systems. Having said that, here are some round trip efficiencies. You can see different types of compressed air, pump thermal. They all fall in this range between 60 and 80%, or I should say 60 and 75%. You can see lithium ion are a little bit more efficient, right, than these thermomechanical systems, but I don't really believe that's important. You can see power density and energy density. What this really means is that it tells us something about the size of the system, right? So for a particular duration, having a small density means that the system is slightly bigger. Again, I don't think this is a very important indicator, but a lot of people mention this. And finally, costs. And one of the things that you'll note here, so we have different power capital costs on this side, energy capital costs on this side, and this is the storage duration of different types of technologies. You can see the blue line, which is really, let's say in inverted commas, the winner in most cases, and that's compressed air, but that's only if you have caverns to pump your air into, which are reasonably low cost. If you really think about it, caverns, however, are geographically restricted, right? So you have to be in a particular location where it's possible to drill cheaply and find a space to store your gas. If that doesn't exist, then compressed air actually no longer is the cheapest solution. It doesn't have the lowest cost. And we shift to other technologies, other thermomechanical technologies, which are cheaper than compressed air, in this case with pressure vessels, right? So compressed air, if you don't have the cover and you have to store the air somewhere, you would have to use pressure vessels, and that's very, very expensive. You can see on these plots, compressed air costs with pressure vessels costs skyrocket. So that's, in my opinion, not really a good solution. And then we have a number of other technologies that I mentioned. It looks as though pump thermal is a little bit lower in some cases than the others. But as I said, there's a huge uncertainty in these costs, so we should take them with a pinch of salt. And the final thing to say is, again, you can see here storage durations, right, that go up to above 100 hours, right? So these red bars that you can see over here is where you would find batteries. And you can see that batteries, you don't go above, let's say, whatever, 5-10 hours typically. And you also have costs in some cases which are higher than what you would have for the thermomechanical systems, even in that a small discharge duration range. So to summarize, I mentioned before, there are advantages to thermomechanical energy storage systems in that they interact both thermally, so they can provide heating, cooling, and/or electricity to sources and sinks. And this is very important in cases where it's not just electricity that you're interested in storing. As I said, there's a very important part of these technologies which has to do with developing some of the components which are very novel, and the costs should be reduced in order for these to become even more competitive. I'm not going to speak a lot about this, but there are a lot of efforts which are ongoing right now to understand what is the value to the electricity system from the penetration of these electricity storage technologies. And there are some studies here that I'm giving to show what would happen if, let's say, liquid air or pump thermal penetrates into the electricity grid in the UK, right? So what does it allow you to do? So you can see that here it allows you to install, let's say, more PV in the south, more wind in the north. You need less CCS and so on. And in terms of challenges, well, I would say reducing system cost is probably the first one. Again, I don't think it's about increasing efficiency, it's more the cost. We need urgently high performance and low cost components, right, which at the moment are under development. And of course, all of these components need to be tested. We have high temperature compressors, reversible machines, so things that can be used both as compressors and expanders. And I think an important thing, note that I wanted to say before sort of closing is, and again, I think most people would agree with this, is, these are multi-scale problems, right? And we need to be thinking across scales to develop technologies which are fit for purpose. So what am I saying here? We have issues within these technologies that go all the way down to what materials are going to pick for the storage, for example, right? And we go all the way up to the whole system where these technologies can be integrated within, let's say, an electricity grid and provide services to that grid and to give benefits to the grid that you're not going to understand unless you model the whole system. So we have this kind of cross or multi-scale problem, and we need to be thinking about how different materials and how different components lead to the design of better technologies, and how these technologies feature within the system, and how they can provide benefits to that system. Thank you very much. Any questions? And thank you all again for inviting me to give this presentation.
Okay, brilliant. Thank you very much for a really interesting talk. So if anyone's got any questions, please direct them to the chat.
I'm not sure how long I took. I'm hoping around 20 minutes.
Yeah, no, that was great. We're almost back on schedule now, actually. So that was perfect. Thanks very much.
Okay, I rattled through it a little bit quickly because I know that we were running a little bit late, but I'm hoping I gave a flavor, right, for things within what what I would call the thermomechanical energy storage community, what the options are, what the variants are, and some of the strengths. I think I'm speaking both to the chair and also to the audience. Again, that there are many different things that you want to be doing when we say energy storage, and in some cases there are technologies within this class of thermomechanical systems which have significant advantages, and we're sort of working on realizing these technologies and making them available.
Okay. So while I wait to see if any other questions come through, I've got a quick one. Right near the start, you mentioned interseasonal storage, and then and then one on your later slides, it looked like certainly for the cavern compressed air, the costs were still falling pretty dramatically once you got over 120 megawatt hour.
Yeah. Right. Sorry. Yeah.
Sorry. Sent you one way and then brought you right back again.
I should have waited. Yeah.
So yeah, that cavernous compressed air, all those lines seem to still be dropping quite significantly once you get to that 120 hours of duration. Is that something that could potentially be for interseasonal storage?
So I should say, so in this plot, right, caverns are this blue line, right?
Yeah.
And there are two costs, and it's actually quite difficult to make sense of these costs. Because they have very opposite trends, right? So the power capital cost, you can see for most technologies goes up with the duration, and the energy capital cost falls. Now you could say, well, what does this actually tell me, and what am I going to take away from this? Well, it depends on the application, right? So the cost that's, let's say, more relevant to you depends on what you want to be doing. But if the energy capital cost is the performance indicator that you care about, the answer is yes. These systems, and this is one of their major advantages with respect to things like lithium ion or generally battery technologies, but not flow batteries. I'm talking about, say, lithium ion and the rest of it, is that their costs per unit something, energy in this case, drop, right, very significantly at larger scale. So we have something called economies of scale, right? And so you're absolutely right. For large systems and for large durations, the costs drop very dramatically. I mean, this is orders of magnitude, right? These are logarithmic plots. And in some cases, so out here, right, this cost is 2 orders of magnitude cheaper than batteries, which are this red block over here. So the answer to your question is yes, absolutely. In the case that we identify applications where we need to store a lot of energy over long durations, there is absolutely no comparison between thermomechanical systems and batteries by orders of magnitude. And so that's why there's a role for these things. Now, in other applications, batteries are the way to go, and there's a lot of investment and a lot of interesting things going on there.
Okay, brilliant. Thanks very much. And we've got one in the chat where it's from Ben Craig, and he says, surely at some point efficiency does matter. So for example, one of the key arguments against using hydrogen as grid storage is round trip efficiencies are well under 50%. Wondered if you got a comment on that?
Yes, yeah. So I mean, of course I agree. I think we're sort of potentially. I will say a sentence that basically encompasses both what I said and what he said, and they're actually not in conflict. Both indicators are important in general, right? Increasing efficiency and decreasing costs both result, right, in an improvement in the overall investment that you have to make. But there's a big but here, which is, from a given perspective, which one of the, if you had to make a 10% improvement to an efficiency or a 10% reduction in cost, which one would have the largest benefit in terms of the whole system, right? So it's not that I'm saying that efficiency, in improving the efficiency by 10% will not have a benefit. Of course it would. But I am saying, and this is clearly the case. I mean, this has been shown in multiple studies and in multiple ways. Decreasing the cost by 10% is always more beneficial to the system than increasing the efficiency by 10%. And the reason for this is actually quite straightforward. The cost of these energy storage systems is much higher than the cost of, let's say, a wind farm. So the cost of increasing the efficiency, right, what it really means is that you have less loss of electricity, right, during this conversion process. So you get 1 unit of energy and you can give as close to 1 unit of energy back, right? If your efficiency is low, it means you need a bigger wind farm because you've lost some of the energy. But the wind farm is cheap, and your electricity storage system is expensive. So you need to target the expense of the electricity storage plant rather than the efficiency of that plant. It doesn't mean that the efficiency is not important. It just means that, in my opinion, the cost is more important than the efficiency.
Okay, brilliant. Thank you. And then there's a couple more coming through. I think we've got time for one more, and then perhaps you could address any further questions in the chat directly. So one from James LaHoo is the cost just machinery costs, or does it include things like land value as well?
Yeah. Oh, very good question. Very good question. Excellent question. So I can see when someone's like already with it and even way ahead of what I've said, because I didn't have time to go into the details. These costs are exactly what was said. They are machinery costs. The true costs would be not just land, not just the price of land. They would be contractual, legal, all sorts of costs that go outside of this. The problem with those costs, and the reason why we didn't include them, is because they're highly variable. So, building one in the middle of nowhere in Algeria and building a plant, outside London, you would have an order of magnitude difference in those costs. So there are typically two approaches that people take. Either you try to be precise with the actual costs, and then you have to start saying where the plant is, what the characteristics of that particular location are, that country, and so on. Or you kind of remove yourself from this specificity, and you just calculate the sort of the basic, let's say, kit itself, in order to allow yourself to kind of be a little bit more general and to say things that don't just apply, let's say, to Algeria, because land is cheap there. So we've taken the latter option, but the disadvantage of this, of course, is that the true costs are going to be higher than this. The assumption that we're making is that those costs would be roughly the same across the technology, so that the comparison does not alter the main conclusions in terms of the comparison that we're making here, right? So that the size of the systems, for example, are not orders of magnitude different that would affect this type of comparison.
Okay, brilliant. Thanks very much. As I say, there's at least one other question in the chat, so perhaps you could address that in there. So in the interest of time, we better move on to our next speaker, which is Harriet Kimpton from the University of Southampton. I'd just like to say again, once again, thanks Christos, for a really interesting talk. So Harriet, if you're ready, I'd like to introduce Harriet, and she'll be presenting the development of a broadband, nope, sorry, that's the wrong title. She's got an updated title, which is the temperature stability and development of a broadband silver nanofluid for solar thermal applications. So Harriet, when you're ready.
Right, hello, can you hear me okay?
Yeah, I can hear you.
Can you see my screen?
I can't see your screen yet,
Hang
no.
on, let's try it. Can you see it now?
Yeah, that's great.
Yeah, let me just put it onto, hang on. Let me just put it onto the main, like that. Can you see that okay?
Yeah, that's great. Thanks, Harriet.
Yeah, okay, right, hello, my name's Harriet, and I'm going to be talking about the temperature stability and development of a broadband silver nanofluid for solar thermal applications. My supervisors are Zunli and Olgan. Right, I'm going to start with an introduction, and then I'm going to go through some experimental methods that were used in this bit of work, some results, and then conclude, followed by acknowledgements. So in overview, there is an unmet need for low carbon heating and hot water. One possible way of meeting this need would be to use enhanced solar thermal energy capture coupled with a suitable interseasonal thermal store. So no electricity involved in this at all. We've heard a lot about electricity, but no electricity with this. This is capturing thermal energy and storing that thermal energy. Today, I'm going to focus on, can I click? I'm going to focus on the enhanced solar thermal capture as opposed to the store side of things. Okay, so how can you enhance solar thermal capture? Well, one proposal to do this is by using a direct absorption solar collector. And here we have, this is a standard collector here, which has got an absorber plate. And this is a schematic of a direct absorption solar collector with a nanofluid in here. So it captures energy directly, and it may be more efficient because of this, but anything you can do to improve the properties of this nanofluid will help to improve the efficiency of the capture of solar energy. So we're going to concentrate on improving the performance of the nanofluid. Right. So one of the issues with nanofluids, metal-based nanofluids have a strong absorption at a low concentration of metal in the nanofluid, but they have a narrow absorption peak, which isn't really what you want. So the aim of this work is to combine a number of different silver nanofluids with a range of absorption properties to give a broadband absorber. And I'm going to focus here today on the development of 3 suitable nanofluids for this, and then assess their temperature stability. I've already published their performance in a simulated sunlight of this broadband mixture, which gave a photothermal energy efficiency of about 85%. And one thing you need to understand what you need to develop. You need to understand a bit about the solar spectra. So here's a picture of the ASTM G173 solar spectra up to 900 nanometers. Now, most of the energy of the solar spectra is in the region below 1300 nanometers. So what you need for your 3 nanofluids is if you can have one absorbing at about 500 nanometers here, you want one absorbing about here at about 650 to 750 nanometers, and you want one that absorbs over here, which we've already developed. So that will be the starting point to develop the other 2 nanofluids. So I did the starting point. Nanofluid 1 is this recipe here. And then I did a lot of changes to the recipe. First of all, looking at what happens if you increase the overall concentration of all the different reagents within the recipe. And then secondly, looking at changing the amount of hydrogen peroxide within the recipe, and then changing the ratio of silver to reducing agent, sodium borohydride, and at that lower reducing agent level to look at what happens if you then reduce the hydrogen peroxide. I then went on and looked at the effect of taking a already produced nanofluid seed and then adding more of the reducing agent to that already produced seed and see what that does to the spectra. And then I looked at adding more of the reducing agent and more silver to the already produced nanofluid. From these experiments, I determined the best nanofluids for nanofluid 2 and 3, and then use the ASTM solar spectrum to design a mixture and combine them together and see what they actually do in reality, and carry out temperature tests on both the mixture and the component nanofluids, removing the samples periodically to measure the UV vis IR spectra. Now, the results, when you change the overall concentration of all the reagents within the solution, this was the original nanofluid that we had developed. The moment you start increasing the concentration, you get a significant dropping in the peak height and a broadening of the peak, with 2 peaks being formed at the higher concentration. So you're no longer able to make nanofluid 1 if you just increase the concentration of all the reagents within the solution. So you're going to need another way if you want to make more concentrated solution. If you change the hydrogen peroxide, you get a blue shift in the position of the peak, eventually producing a single peak over here when no hydrogen peroxide is present, which corresponds to the formation of silver nanospheres. But it's not possible to make anything in this 500 nanometer range here. So if you then reduce the ratio of sodium borohydride to silver, you can make a nanofluid with a high absorption peak at about the 650 to 750 range, which is of the same concentration as this one over here. So you can see the effect of reducing the ratio of silver to sodium borohydride. So we've got a contender now with this C1 here for nanofluid 2, which is great, but we still haven't got a recipe that gives us anything in this 500 nanometer range for nanofluid 3. So what happens if we add the reducing agent to the already formed nanofluid C1? Well, you get a blue shift towards the 500 peak that you're looking for, but you also get a drop in height of the peak as you are adding more liquid to the solution, so this isn't the most suitable recipe for nanofluid 3. So you can blue shift it, but you getting a drop in peak height, so that's not the most suitable. Now, if you add more silver as well, you get a shift where you want to about the 450 to 550 range here. You get a drop in peak height, but this is measured at a much higher dilution rate to make sure we didn't saturate the spectrometer. So this would be a suitable recipe for nanofluid 3. So now we've got a recipe for nanofluid 1, which was A1, nanofluid 2, which was C1, and nanofluid 3, which is E2. I choose, because there's not much difference between E1 and E2, I chose E2 because it contains less sodium borohydride. And then using the ASTM spectra, I designed a recipe which consisted of 50% A1, 20% C1, 30% E2. Right, now what happens when we heat the component parts of this? When we heat the nanofluid 1, we get a blue shift in the spectra after an hour, which stays about the same over the 12-hour period. So, and that's about a 50 nanometer blue shift, which is less than the blue shift that we saw on simulated sunlight testing of 100 nanometers for this nanofluid. If we heat nanofluid 2, we get a larger shift, blue shift, in the position of the maxima by about a 90 nanometer blue shift after an hour. This is similar to what we saw for this nanofluid in simulated sunlight tests after only 30 minutes, because the simulated sunlight test is probably a more harsh environment than temperature alone. If we heat nanofluid 3, we get a different response. We don't get a shift in the peak, but we get an increase in the peak height. This is similar to what we saw in simulated sunlight testing, but in simulated sunlight testing, we saw a red shift in the position of lambda max and a larger increase in the height. And now, if we look at the mixture, we get, this is the mixture. The blue line here shows the mixture before testing, and you can see a little shoulder here corresponding to nanofluid 2, that's the nanofluid 3 peak, and that is the nanofluid 1 peak here. And with temperature testing, you get an increase in the overall peak height, you lose that shoulder corresponding to nanofluid 2, and you get a blue shift in the shoulder corresponding to nanofluid 1. So if I then summarize the temperature results for the component, the 3 component nanofluids, and look at the repeatability, there's quite good repeatability between samples. And you can see that the largest change, which happens in the first hour, is for nanofluid C1, which was nanofluid 2. You can see that nanofluid 3 has no change in the peak, and that the change occurs mainly within the first hour of temperature testing. So in conclusion, I was able to develop 3 different nanofluids containing silver with distinct absorption profiles and combine them together. This study, along with our previous publication, are the first to make and test experimentally a broadband absorber based on silver. It's the first study to investigate the effect of temperature alone on the absorption spectra, and there's an initial rapid change with temperature exposure for the components and for the mixture. So therefore, in conclusion, without further stabilization, the developed broadband absorber, although it gives a good performance, would be unsuitable for solar applications because of this instability, both to temperature and as previously reported, to natural sunlight. This study also highlights a lot of the difficulty in investigating and controlling the nanofluid synthesis because it's a non-linear change with things like concentration, and the ratio of the different reagents has a significant effect on the nanofluid produced and the solar spectrum obtained. I'd like to acknowledge the Facility of Engineering and Physical Sciences at the University of Southampton for supporting this work, and the CDT and energy storage and its applications. Right, thank you. Any questions?
Okay, brilliant. Thanks very much, Harriet. Good on the timing there. So one straight away from James LaHoo says, thanks, Harriet, for a really interesting presentation. Do you think it's possible to suitably stabilize the nanofluids for use in solar applications?
Hang on. Yes, it may be, but I think that it's going to be a very tall order to do this because the environment on a roof for a solar collector, it needs to be stable for like 20 years. And I don't think even with, silver's one of the worst cases because it is light sensitive, and you can stabilize or try and stabilize by coating with silica or something like that. But even then, I think that they won't meet that challenging environment. And I think even something like carbon, you're going to have problems because it's as a fluid on the roof, and that would be very difficult to stop aggregation with time of the carbon particles and keeping them as a nano solution. So I think it's probably that, although the idea of using a direct absorption solar collector with a nanofluid sounds lovely in practice, I really think it's going to be a very, very tall order to make something that is actually commercially viable. Okay,
brilliant, thank you. And then just a quick one from me. You said, I think it was on slide 9, but when you added both the silver as well, you said you diluted it. Do you know what effect the dilution has? Is it linear, or is it? Have you any idea what the relationship between diluting it and?
Let me just go back to the screen save and get to slide. Hang on, let me just go back to slide 9 and make sure we're talking about the same thing, because I had to dilute, because the when you test you have to dilute all of the samples that are above a certain amount to keep the absorption spectra below what the machine will read. Okay.
Yep.
I think there is probably some effect of diluting on the stability because you're adding water to it, but I have looked to some extent at doing dilute versus more concentrated solution for temperature stability testing, and the more concentrated solutions tend to be less stable.
Okay, and in terms of the absorbance, so you said because it's diluted, your absorbance is lower. So if it's diluted 1 to 5, it was diluted less, would it?
It's actually, I should have diluted it 1 to 4.7-ish because of the molarity of that one to give a comparable plot.
Okay.
Okay.
Right. Okay, brilliant. Thanks very much.
Thank you.
Okay, if there are any other questions, again, put them in the chat, and Harriet, maybe you could have a look and
Right, let me
address
stop
them in there.
sharing again. Hang on, there we go.
So yeah, that's all that's come through to me, but thanks very much again, Harriet. So is our next speaker ready to go? Ahmed Al-Mudhafar from the University of Sheffield.
Yes.
Yep, okay, ready to go. So brilliant, thank you. And today you're presenting enhancing the thermal performance of phase change materials in a shell and tube latent heat energy storage system by utilizing innovative fins. So brilliant, thanks when you're ready.
Yeah. Did you hear me, please?
Yeah, we can see that now, thanks.
And can you see my slides?
Yeah, that's perfect.
My presentation title is Enhancing the Thermal Performance of Phase Change Material in a Shell and Tube Latent Heat Thermal Energy Storage System by utilizing innovative fin. My name is Ahmed Al-Mudaffar. The content of my presentation is introduction, problems and background, objectives, result and conclusions. The problems is global warming, greenhouse gas emissions and air pollution, and usage of finite resources. Motivation, the need to develop an effective thermal energy storage system to fill the gap between the existing energy supplied and the demand. Latent heat thermal energy storage method by using phase change material have two advantages: high energy storage density and nearly isothermal storage process. In recent years, phase change material have received considerable attention in various applications, which include solar thermal energy storage, waste heat recovery, energy efficient building, and cold storage. There are many methods for thermal energy storage, which include sensible heat storage, shown in the figure, which stores the heat in the material by changing the temperature of the material. And there is latent heat storage, stores the heat in the material during the changing the phase of the material. And the third is thermochemical reaction. Latent heat thermal energy storage by using phase change material. What is the phase change material? Phase change material is a substance with high latent heat of melting. Latent heat is absorbed or released when the material changes from solid to liquid and vice versa. When phase change material absorb heat and raise their melting temperature, they absorb large amount of heat at an almost constant temperature. The phase change material continue to absorb the heat without a significant rise in temperature until the material is transformed to liquid phase. Phase change material stores from 5 to 14 times more heat per unit volume than sensible heat storage material such as water, masonry, or rock. In the literature, there is a growing number of studies which analyzes using phase change material in thermal energy storage application. The investigation highlighted the following. Most phase change material with high energy storage density have low thermal conductivity. So heat transfer enhancement techniques are required for any latent heat thermal energy storage application. The objectives. The main challenge of using phase change material in thermal energy storage is their low thermal conductivities. This leads to increased energy storage release times. Also, considerable research has been devoted to utilizing fin to improve the thermal performance of phase change material thermal energy storage system. Rather, less attention has been paid to the geometric design of fins. The geometric design of fins has a strong influence on the energy storage release time for thermal energy storage system based on phase change material. In this study, numerical investigations were carried out to improve the thermal performance of phase change material in shell and tube heat exchanger by using 3 types of fin, longitudinal and T and 3. The T-fin shape was introduced as a unique extended surface to enhance the heat transfer between the heat transfer fluid and the phase change material, which contains some materials compared to the familiar longitudinal fins configuration and could be more efficient compared to popular fins. Technique used to enhance the thermal conductivity of phase change material. Most phase change material have poor thermal conductivity, leading to increase the charging and discharging rates. The heat transfer thermal performance of phase change material can be enhanced by using finite tube, insertion of metal matrix into the BCM, dispersion of high conductivity nanoparticles, and encapsulation of BCM, and using melted tubes. This is the technique used to enhance the thermal performance of phase change material. The governing question. In this study, the enhancement of thermal performance by using an innovative T-fin shape numerically investigated to evaluate the thermal performance of the suggested fin. It is thermal performance.
Oh, I think we might have lost Ahmed there. So hopefully he'll be coming back in a second.
Now, did you see the presentation, please?
Yes, yeah, we can see it again. I think you were a slide or two behind that though when I lost you anyway.
Yeah, this figure shows the geometrical model, 3-dimensional model, and the cross-sectional area of the model used in the simulation. This is a shell and tube heat exchanger, where the heat transfer fluid passes through the tubes and the BCM in the shell side, and here the fin. This figure shows the computational domain with the indicated boundary condition for the shell and tube. This is the boundary condition. Here the heat transfer fluid temperature, and the outside boundary condition is insulated, adiabatic boundary condition. This is the properties of phase change material used in the simulation. This is the different fins configuration and dimension. The first one is longitudinal fin, and the second one is the T-fin shape, and the third one is 3-fin. This is the computational domain for various heat exchanger with different fin configuration. The first without fin, the second with T-fin, and the third with longitudinal fin, and the last with a 3-fin. This figure shows the liquid diffraction comparison for melting process between heat exchanger with various fin shapes and without fin. It is clear from this figure that when using the T-fin shape, the phase change material process accelerated. This happened due to the increase of heat transfer surface area and increase of thermal penetration depth. This figure shows the liquid diffraction contours at different times for melting process comparison for various fin shape from left. This is without fin, and the second with T fin, and the third by using longitudinal fin, and the fourth with using a tree fin. It is clear from this figure that the melting process accelerated in case of using the T fin shape compared to other fin shapes. This figure also shows the contours of temperature at different times for melting process comparison for different fin shape in case of without fin, and the second one with using T fin, and the third with longitudinal fin, and the last with using a tree fin. Conclusion: most phase change material with high energy storage density have low thermal conductivity, so heat transfer enhancement techniques are required for any BCM thermal energy storage applications. Many novel fin shapes were introduced to enhance the thermal performance of phase change material in shell and tube. These shapes included T and tree fins. When utilizing the T fins, the phase change material melting time reduces by 33% as compared to the case of using longitudinal fin. This acceleration in melting process when employing the T fins was due to the increase of the heat transfer area and increase of thermal penetration depth. Thank you. And any question, please?
Okay, brilliant. Thanks very much. Some interesting results there. So again, I direct everyone to the chat. So one from James Lahoo. It says, do you have any plans to build an experimental rig to validate your simulation?
Maybe in the future I will do that. But this result is part from my PhD thesis. I use numerical simulation to do it, and I compare with other people numerical, other people experimental work.
Okay, brilliant, thank you. And one from Nick Hillier says, for a symmetric fin design in cavity, can you explain a little more regarding the asymmetric melt seen over time?
What please? Can you repeat the question, please?
So I think if you go back to a couple of slides, but it says, for a symmetric fin design and cavity, can you explain a little more regarding the asymmetric melt seen over time? So spatially, you've got a different melt at the top and the bottom there.
Yes, it is happen that at the top of the shell and the tube, it is due to the natural convection. The melt process accelerated at the top, while at the bottom it is delayed because of the natural convection process.
Okay, brilliant. Thanks very much. And just a quick one from me as well. So is there any difference in terms of ease of manufacture or cost perhaps of the fins to consider as well? Obviously the T fins seem to perform significantly better than the others.
I think there is no difficulties in manufacturing this shapes of fin, and also it is used the same material, but the design is different.
Yeah. Okay. Brilliant. Okay, thanks very much. And thanks very much for some great answers as the question and a really good talk.
Thank you very much.
I'd just like to say thanks again to all of our speakers in this session. And now I believe it's time for lunch, and we'll reconvene again here at 1 o'clock after lunch.
Thank you.
Thank you.